Welcome to Brain Vision.
Okay, so for this problem, we have another process where we have a PV diagram, some changes happen, and you have to kind of fill in the blanks for different quantities in broad strokes. So for the first, so here's the PV diagram, and the first question asks, find the pressure at point A. So how can we find the pressure? Well, I would say we should do this based on the knowledge that from A to C is isothermal. And so if for an isothermal process, PV stays the same, that's because it's equal to nRT. And then all of these stay the same for an isothermal process, assuming, of course, that the container is closed and you don't lose your N. So therefore, you can say PAVA equals PCVC. And that's equal. And so that, or not equals, but that implies that PA equals PC times VC over VA. And so if you plug in your numbers, you have P at C, we know, and we know each of these volumes. And I was kind of sloppy with the units, but it's in the book. I didn't want the page to get too cluttered. So if you do that, and you don't even need a calculator, since the volume just increases by a factor of 4, that means the pressure will also increase by a factor of 4. So they're proportional. So it's 8 times 10 to the 5 pascals. Awesome. And for part B, T at A is equal to PV over NR. Oh, sorry, I didn't even read what it was. Okay, so B, find the temperature at A, B, and C. So yeah, I started with A. And so, yeah, we just want to use the ideal gas law, PAVA over NR. And if you just plug in all your numbers, 296 Kelvin. So yeah, our PA is the 8, VA is 0.01, and N is your 3.25, and then R is 8.315 joules per mole Kelvin. I guess I can write that. Equals 8.31 joules per mole Kelvin. Great. C, what is asked for in C? How much heat entered or left during like all the segments? Oh, oops, I didn't finish finding the temperatures. Sorry. So that's TA is that, and then that's equal to TC. So TC equals TA, of course, because it's an isothermal change. And to get TB, you can just do the same thing. TB equals PB. Got that. So the same as PA. VB. Got that over NR. And then when I calculated that, I got 1184 Kelvin. Okay. Funny shape. It's okay though. For C, now we want to find all the Q's. So the equation we want to use is Q equals delta U plus the work done by the gas. And then I'm going to actually, this is fine. So Q is that in general. So now we want to do it for each case. So for case A to B, we want to say QA is equal to delta U there, and delta U is N CV delta T. And And if you look up CV, it's 12.47. I'll go ahead and put that in our constant box. CV equals 12.47. Oh, it's getting so messy. Sorry. Okay. So, but we have everything we need there. And then the work plus the work done by the gas, which is P delta V for a constant pressure process. And then that's of course V at B minus V at A. And delta T is T at B minus T at A. If you plug that into a calculator, then maybe you'll get what I got, which was 60,000 joules. All right, this is going to be messy. I really don't want to lose this page, but I guess to prevent it from being a total mess. Well, let's see. Let's see if I can fit some more on here. So for BC, again, we'll just use the same equation. Oops, I put QAB. Okay, QBC. Okay, that one's nice because delta V is 0, so it's just going to be NCV T at B minus T at C. We have both of those from part B, so we really kind of set us up sort of nicely to do these problems. All right, and then C at A, yes, I'm going for it. Then Q is equal to, let's see. Okay, so it's isothermal, so then our delta T term kind of dies. And so, yeah, so then it's just going to be, so for an isothermal process, the work is nRT ln of V at A over V, oops, no. Okay, V at C. And if you plug in all of that, then maybe you'll get what I got, which is minus 11,000 joules. And is there more? But wait, there's more. Yes, there is more. So for part D, it asks for all the changes in internal energy. Okay, we kind of just calculated that. For Q, maybe there was some other way you were supposed to find Q. And like this is, I usually would just do this on another sheet, but I know it's actually pretty short, but to make this less confusing, I'll give it its own little color. So yeah, we of course want to use the equation U is NCV delta T. So for AB, then it's NCV, oops, NCV, that's not a subscript, there we go, NCV TB at TA minus TA. Okay, actually highly regretting doing all this on one. I'm just gonna rewind this and do it on the next one or on a separate board. Okay. Oh, and I can write nice and big now. D. U equals NCV delta T. So then for A to B, that's N, whoops. I don't know why I want to make that a subscript, but I do. And if you plug in all the numbers, then you got 36. Something happens with this. 36 kilojoules if I go too fast. From B to C, then it's the same thing, but negative. So minus 36K because it's isothermal. So T at B equals, oh, excuse me, let me go back to the other board. T at A equals T at C. So yeah, so it's the same calculation, but reversed. So it would be T at C minus T at B. And for Ca, of course, if it's isothermal, then U equals 0. U equals. Okay, awesome. Oops, let me put my J there. Kilojoules.